All right, this is the final video for the week. It's going to specifically talk about solubility of gases. Last video, sorry, I talked about solubility of solids specifically, and all the curves, solubility curves you've looked at so far, dealt with when ionic compounds or solids are dissolved in water. For gases, though, things change a little bit. Just to lay down on the table, if you saw a solubility curve of a solid, we've always seen a general exponential typically. There were some that was a little bit more linear, but mostly it's always sort of going up. When we talk about gases, it's a little bit interesting. It has nothing to do with the compound itself. It has everything to do with the state. The solubility curve is going in a downward fashion. Okay, and in page 395, it gives you a solubility curve of oxygen in water, but just to make things a little bit more applicable to you and a little bit more, makes more sense, I'm going to talk a little bit about carbon dioxide. Think about, just literally, just close your eyes if you want, whatever. Think about your favorite brand or favorite pop. Okay, could be Coke, could be Sprite, could be Mountain Dew, could be C+, could be Fanta, could be whatever, okay? What happens when you shake it? Well, bubbles release. What happens afterwards if you pop off the bottle? The bubbles will fizz out and make a big mess, right? That's obvious stuff. That is the gas that was dissolved. That's a carbon dioxide that was dissolved in the drink, that when you shake it, it was able to release itself from its aqueous sort of, I guess, its solvent. It was able to escape from the water surrounding it. That's the key point. What happens though if I take a cup of the pop I just poured, it has all the carbon dioxide in it, and I let it sit on the kitchen counter, giving it time until it becomes room temperature? What happens? Well, it becomes flat. It becomes gross. It becomes this syrupy liquid that you probably don't want to drink unless you're addicted to sugar, okay? And why is that? Normally, you would think that when temperature rises, the solubility increases. But for gases, the solubility, so what do you call it? So normally, if the temperature, so right now, let's say, what is it? Refrigerator temperature was 3 degrees. It was able to dissolve a lot. But if we wait until the room, it hits room temperature, the amount of carbon dioxide that can dissolve in the water is a lot less. So this, let's say, is 3 degrees. This, let's say, becomes 25 degrees. The left cup of pop has more ability to keep the carbon dioxide dissolved inside the solvent. When it's heated, it loses that ability, and all the carbon dioxide is lost. To understand why the relationship is a little bit different, I'm going to have to get you to visualize just the idea, once again, of what it means for a solute to be dissolved in a solvent. Here is my carbon dioxide molecules, okay? And around it are the water molecules. And of course, they're not static. It's not just sitting there. They are all sort of moving about like crazy, okay? And this is at 3 degrees, 3 degrees Celsius, okay? If this cup of pop warms up, in other words, it gains more heat, it gains kinetic energy, then the movement of these molecules will begin to increase. And what do we say about the space between the molecules as they are beginning to move around like crazy? Move around like crazy. What happens to the space? It increases. Well, normally if this is a solid and, you know, normally, let's put it this way. If you were a person, right, and these molecules or these platforms are supporting you, What if these two platforms gave way from underneath your feet? What happened to you? Gravity would plummet you down. But what if you weren't a human being, but rather you were a gas molecule that was sort of supported, or rather, it kept you from flying out? What if these two platforms that were keeping you trapped in suddenly disappeared because they were moving too fast? Well, gravity doesn't affect you. As a gas, you would lift off. That's exactly what's happening here. Okay? So, as water molecules move around, they have a lot more kinetic energy. The gas molecules will be able to escape from the natural intermolecular forces of the water, okay, and leave the solution. And as it gets hotter, that is why there is less ability for the gas molecules to be dissolved. That's pretty much it. This is one of the main reasons why things like climate change becomes really, really, really concerning. Here's an example. If this is let's pretend this is the ocean. Inside the ocean, being a body of water, it has lots of gases dissolved in it. One of those gases being carbon dioxide. Some of those gases could be even things like methane and a whole bunch of other things. If climate change causes the temperature of the water, temperature of the world to increase, what happens to the body of water in the ocean? Well, it evaporates. Even before the evaporation, though, the water molecules begin to move like crazy. And when that happens, what happens to these gas molecules that are trapped? Well, they escape. One of the gases that will escape is carbon dioxide, which is a naturally produced greenhouse gas. This will cause, I guess, very simply, more insulation of the entire Earth, which will cause the temperature to increase again, which will cause more carbon dioxide to release because the body of water is warmer, which causes more greenhouse gases to be present, which will cause, you get the point. It keeps on going in a circle, causing a positive feedback loop. Hey, going back to grade 9 science, everything connects. Please take a look at pages 395 and 396, which discusses shortly, in a short, concise manner, how the solubility of gases is completely different, completely opposite rather, of solubility of solutes. And then go ahead to page 397. This is chapter 8's, so I guess 8.5's review questions. Try numbers 2 to 5 and number 9. See if you can answer some of those questions. And a quick disclaimer, you must, by the end of this week, be familiar with chapters 8.1 to 8.3, as well as 8.5. These have nothing to do with the math per se, and it has everything to do with understanding solubility and how it works. Next week, we are going to look heavily into the math portion using the information that we have learned about solubility. Okay? So again, this week is going to be largely just get the big picture of things. Next week, we will look at the math. Do your best, ask me questions, hang in there, and I hope to see you soon as always.